The tabulate and mean commands are used for exploratory analysis, descriptive statistics, and when generating new variables. This lecture covers three descriptive statistics: means and medians, which are used to summarize continuous data, and percentages, which are used to summarize categorical data. The mean, or average, is calculated as the sum of values divided by the count of values. Means are used to describe variables that are normally distributed. Here is an example of a normally distributed variable. These are the ages of 10 university students. We see that their ages take on a bell-shaped distribution. When the data are normally distributed, half of the data values are larger than the mean, and half of the data values are smaller than the mean. In variables that are not normally distributed, the values are skewed or have one long tail. In non-normally distributed data, the mean is influenced by extreme values, and therefore the median, the center value if you lined up all the values from low to high, is a more useful descriptive statistic than the mean. If we lined up all of the values from lowest to highest, the median would be at the 50th percentile mark. If there are an odd number of values, the median will be the central number if you lined up the values from lowest to highest. If there is an even number of values, the median will be the average of the two central numbers. Percentages are used to describe categorical data and exist on a scale of 0 to 100. Percentages are not to be confused with proportions, which exist on a scale of 0 to 1. The percentage is the proportion multiplied by 100. Proportions are calculated from a binary response. A characteristic is present or not. A proportion is the mean of a binary response. It is the count of observations that have the characteristic of interest divided by the total count of observations, and we multiply this by 100 to get the percentage. Percentages are used to describe all categorical variables, including binary, ordinal, and nominal variables. Binary variables have two values, usually coded as 0 and 1. Ordinal data are categories that follow a logical order, like education level, and nominal data are categories that do not follow a logical order, like marriage status. In variables that have more than two categories, we can think of each category as having a binary response, and we calculate a percentage for each category. Variance is related to precision, or level of understanding. The variance describes the amount of spread around the mean of a variable. For normally distributed continuous data, and for binary data, spread is summarized as standard deviation around the mean. For skewed continuous data, spread is summarized as interquartile range around a median. If you lined up all values from smallest to largest, the interquartile range includes values between the 25th and 75th percentile. In survey data analysis, we usually do not present standard deviations or interquartile ranges. Instead, we present 95% confidence intervals. While the confidence intervals are influenced by the spread of data values in our sample, it actually represents the spread of means in a hypothetical situation where we select multiple samples from the same population. We are concerned about this mean of sampled means because by chance any one sample might not perfectly represent the underlying population. One way to think of the 95% confidence interval is to imagine that we drew 100 independent samples from the same population and made 100 different means. The mean in each sample would be slightly different due to chance. The 95% confidence interval would be the spread of the middle 95 means. The 95% confidence interval represents a range of values that we are almost certain contains the real mean in the population. Stata calculates 95% confidence intervals for means and percentages. Stata will assume that any continuous variable follows a normal distribution. For continuous data that are not normally distributed, you should either 1. Mathematically transform the values so that they take on a normal distribution, for example by taking the square root, or 2. Categorize the values. Transformation of the continuous values is outside of the scope of this course and is not typically done when analyzing categorical outcomes. I recommend that you categorize all values because it addresses any issues of skewed distribution, but it also simplifies interpretation, which we will discuss further in the logistic regression videos. In non-survey data, we can perform analysis in subpopulations by excluding or dropping observations that are not in the subpopulation. You cannot drop observations in survey data analysis, or your variance estimates will be biased. In survey data analysis, we must analyze data according to the sample design. If the sample is designed to be representative of women age 15 to 49, but we are only analyzing women age 15 to 24, we still need to keep women age 25 to 49 in the dataset. The statistical reason is that Stata needs the total number of observations in the dataset, the number of observations according to the sample design, in the denominator of the variance estimator. If we drop some observations, the variance will be incorrect and could lead to incorrect answers to our research question. The correct way to perform a subpopulation analysis with survey data in Stata is to specify the subpopulation in an SVY : statement. We create a new variable where 1 is equal to the subpopulation and 0 is equal to not in the subpopulation. This way, Stata knows to use only the subpopulation data in the mean estimator, but will still count the total number of observations according to the sample design for the variance estimator. Before performing descriptive statistics with survey data, we must specify the sample design in a survey set statement. Watch the survey data analysis video at www.populationsurveyanalysis.com to review this command. The survey set statement is absolutely essential before performing descriptive analysis with survey data. To describe a continuous variable in Stata, we start by looking at the shape of the distribution in a histogram, so that we can decide whether to move forward with a mean or median calculation. We have the kids' recode file open. Let us compare two continuous variables, mother's age, M-age, and household wealth score, H-H score, so you can see the difference between a normal and a skewed distribution. Do you see how the distribution of mothers' ages makes a nice bell-shaped curve? This is what a normal distribution looks like. You can use either a mean or median to describe the center or average of this distribution. The mean is the conventional statistic used to describe a normally distributed variable. Household wealth scores, on the other hand, do not follow a normal distribution. These scores are calculated from a principal components analysis. The scores range from -163,000 to +680,000. The scores themselves do not mean anything, but the relationship of the scores to each other are important. A household with a score of -2,000 is wealthier than a household with a score of -20,000. We see that the household wealth scores are skewed. The upper tail is much longer than the lower tail, which means that there are a small number of people who are very rich and a concentration of people who are poor. If we calculated mean household wealth score from this distribution, the mean score would be higher than 50% of the population because a few rich people are outliers and strongly influencing the mean upward. For skewed variables, either transform the values so they follow a normal distribution, or as I recommended earlier, categorize them. Before calculating the mean or median, we check the code book for each variable to see how missing values and don't know responses are coded. Sometimes missing values are coded as 9 and don't know responses are coded as 8, and we should recode these as missing before performing descriptive analysis. Neither of these variables have missing or don't know categories, so we are okay to move forward. Calculation of the mean is quite easy. Since we have specified the survey design above in a survey set statement, we can tell Stata to apply the survey design to our analysis with an SVY : statement. Then we type mean and the variable, in this case M-age. The average age of mothers who have a child under 5 in Rwanda is 30.6 years, rounded. We are 95% sure that the real mean age of mothers in the population is between 30.5 and 30.8 years. You need only add the subpopulation option to the mean command, like this. To calculate the mean and 95% confidence intervals in a subpopulation, write comma, subpop, parentheses, variable name, after SVY and before colon. So the mean age of mothers who have a child under 5 in Kigali, not all of Rwanda, is 29.6 years, with a 95% confidence interval of 29.0 and 30.2 years. We describe categorical variables with percentages using the tabulate statement. For example, to describe the percentage of children who live in households that cook with charcoal, we would type SVY : tabulate variable name. To display percentages between 0 and 100, rather than proportions between 0 and 1, we add the option %, and to estimate the 95% confidence intervals, we add the option CI. 8.7% of under 5 households cook with charcoal in Rwanda. To estimate a percentage in a subpopulation, simply add the subpop option after SVY and before the colon. When we perform the same analysis in Kigali only, we find that 64.7% of under 5 households cook with charcoal. The mean and tabulate commands allow you to describe the means and 95% confidence intervals of a single variable in the population or subpopulation. Go to populationsurveyanalysis.com for a PDF version of this video and other learning materials that support your analysis of a population survey dataset.